A photograph captures a static state, while the rippling water beside it represents a process. Machine learning depends on following processes, not observing still moments. A data snapshot reports where a value is right now, but it hides its direction of movement or its speed of arrival. To study movement, we convert observations into vectors, structured numbers representing a point in space. This circle's position is defined by x and y values. Tracking these vectors over time forms a trajectory. This trail reveals system behavior, turning isolated measurements into predictable paths. Storing this history is only the first step. A model begins to learn only when it makes a prediction and identifies a specific failure. Imagine rolling a ball down a ramp toward a target cup. If the settings are wrong, the ball stops short or overshoots. We quantify this error using a loss function. This mathematical tool measures the distance and direction of the mistake, turning a miss into a number the machine can reduce. By measuring this gap between the current prediction and the intended target, the system generates the feedback it needs to adjust itself. A steep stone staircase and a gentle winding ramp arrive at the same terrace. Even though the destination is the same, each path demands a different amount of effort. We measure that demand as slope, a fair comparison of how much height is gained for every meter of forward movement. AI data rarely moves in straight lines. It exists on complex curves where the steepness changes at every single point. Finding the lowest ground requires reading the local direction of the curve. Like a bead in a bowl, it must know which way is down. The derivative provides this local compass. It measures the sensitivity of the error, asking exactly how much the loss will change if a specific setting is moved a tiny amount. This is like adjusting a radio dial. One direction might increase the static, while the other makes the signal clearer. The derivative identifies which direction clears the noise. This provides the critical instruction for the system's weights, indicating exactly which way an individual parameter must move to lower the total error. A single dial is manageable, but modern systems must coordinate adjustments across millions or billions of controls simultaneously. Mathematics manages this scale through the gradient. The gradient collects every individual derivative into a single vector, representing the unified direction of change for the entire system. In this wireframe landscape, the gradient points directly down the steepest available decline. It provides a direction map for the entire error surface. The algorithm that follows this map is called gradient descent. It uses that directional information to physically update the model's numbers, one step at a time. Because the model cannot see the whole landscape at once, it moves like a hiker in thick fog. It calculates the slope under its current step and moves cautiously toward lower ground. Optimization moves through this landscape by repeating a simple cycle: calculate the local slope, take a measured step, and reassess the result. In a multi-stage process, an action at the beginning of the chain has a direct downstream consequence for the final result. While the flow of data travels forward, the responsibility for correcting a mistake must travel in the opposite direction. We use backpropagation to manage this. By applying the chain rule, the system traces the final error backward through the network, assigning the appropriate amount of correction to every parameter that influenced the outcome. This backward signal is how large language models learn to predict the next word in a sentence. Every fluent choice rests on millions of these invisible, calculated adjustments made during training. This creates a dependable loop. Vectors organize the data, matrices transform it, and gradients pass the loss backward to refine the model's internal settings. Training is the continuous application of these mathematical steps to turn a recorded error into a corrected parameter. Accuracy emerges from the consistent, disciplined measurement of change.